Every time you pick up your phone or turn on your computer, you're tapping into the power of billions of tiny, invisible components. Well, today, we're going to pull back the curtain on one of the most important of them all, the PN junction diode. Let's dive right in. So everything in electronics really boils down to this one simple but really important question. How do you build a one-way street for electricity? How do you make sure that current goes exactly where you want it to go and never, ever flows backward? Well, the answer is the diode. You can think of it like a microscopic gatekeeper, or maybe a one-way valve for electricity. It's a tiny component, but it has one critical mission: let the current through one way and slam the door shut if it tries to come back the other way. And the workhorse, the most common type you'll find, is the PN junction diode. It's a super simple device, just two terminals. But its ability to control the direction of current is, and I'm not exaggerating, what makes all of modern electronics possible. So, how do we actually build this thing? It all starts with a semiconductor, usually good old silicon. But here's the thing, pure silicon on its own is, well, it's kind of boring. We have to tweak it, give it some special properties, using a process that honestly sounds like something straight out of science fiction. That process is called doping. And no, it has nothing to do with sports. In electronics, doping is when we intentionally add just a tiny amount of specific impurities into that pure silicon crystal. And doing this completely changes how it behaves, letting us create two very different flavors of silicon. So, these two flavors are P-type and N-type. For P-type, think positive. We've doped it to create a bunch of holes. Just imagine a parking lot with a ton of empty spaces just waiting for a car, or in this case, an electron. These holes act like positive charges. Then you've got N-type, for negative, which we've doped to have a surplus of free electrons just buzzing around ready to move at a moment's notice. Okay, so we've got our two special types of silicon, P and N. Now comes the really cool part. What in the world happens at the exact moment we bring them together and form that PN junction? It is instant, beautiful chaos. All those free electrons on the N side, they see those empty parking spots, the holes, on the P side, and they just can't resist. They rush across the junction to fill them up. We call this diffusion. And as soon as an electron finds a hole, they recombine and neutralize each other. But wait, here's the twist. Think about it. The atoms on the N side that just lost an electron, well, now they have a net positive charge. And the atoms on the P side that just gained an electron, you guessed it, they have a net negative charge. And the kicker is, these new charged atoms, these ions, they're locked into the crystal lattice. They can't move an inch. So what you get is this zone right at the junction that's now totally empty or depleted of any charge carriers that can actually move. This is the depletion region. And this is the absolute genius of it all. It's a barrier that builds itself with no moving parts. It creates its own little electric field that stops any more electrons from crossing. The gate has literally just slammed shut on its own. So we've created a natural barrier that stops current. Okay, but how is that useful? Well, the real magic, the part we control, happens when we apply an outside voltage. We can either use it to shrink that barrier and open the gate, or we can use it to make the barrier even bigger and lock it down tight. This is called biasing. And that gives us two options. We can hook up a power source one way to create what's called forward bias, which shrinks the barrier and lets the current flow. Or we can hook it up the other way, create reverse bias, which makes that barrier even wider and stops the current cold. All right, let's look at forward bias first. This is how we get our diode to actually do some work, to open that gate and let electricity flow right through. So to do this, we connect the positive end of our battery to the P-type side and the negative end to the N-type side. And you know what they say, opposites attract, but likes repel. The positive terminal shoves those positive holes forward, and the negative terminal pushes the negative electrons forward, forcing them both right towards the junction. This external push is so strong, it just completely overwhelms that little internal barrier, and that depletion region basically disappears. And what's the result? Well, with that barrier out of the way, you get a massive flood of charge carriers pouring across the junction. It's a live transfer of charges. Electrons go one way, holes go the other, and together they create a powerful electric current. The gate is officially wide open. Okay, so what happens if we flip the battery around? What if we try to push the current the wrong way? This is reverse bias, And this is how the diode becomes a locked gate. So this time, we connect the positive terminal to the N side and the negative to the P side. Now, instead of pushing everything together, the battery starts pulling the charges apart. The positive terminal yanks those free electrons away from the junction, while the negative terminal pulls the holes in the other direction. This literally starves the junction of charge carriers, making that depletion region grow even wider and stronger than before. And that's the whole point. This bigger, stronger barrier becomes a massive roadblock. It acts just like an insulator, with a super high resistance to current flow. For all practical purposes, no current can get through. The gate is now bolted shut. So we've seen the how. We know how to open and close the gate. But now let's talk about the why. Why is this simple little one-way trick the foundation for pretty much all modern technology? This graph, the VI curve, tells the whole story perfectly. Look over here. On the left, that's reverse bias. As we increase the negative voltage, what happens to the current? Almost nothing. It's flat at zero. The gate is shut. But then, look at the right side. We apply a little positive voltage, a little more, and then, bam, we hit a point called the knee, and the current just shoots straight up. The gate flies open. And for a typical silicon diode, that knee voltage, the little push it needs to open the floodgates, is only about 0.7 volts. That's it. It takes such a tiny amount of energy to unlock a massive flow of current. So why does this all matter? Well, its number one job is rectification. That means turning the alternating current, or AC, from your wall outlet into the direct current, DC, that all your gadgets need to survive. But that's not all. Diodes are in radios detecting signals, they're used to regulate voltage, and it can even be made to emit light, that's an LED, or detect light, which is a photodiode. But really, it all comes back to this one single powerful idea. This ability to be a one-way street for electricity is, without a doubt, the diode's superpower. It's what makes it so essential. So we've seen how putting two special layers of silicon together creates this incredible one-way gate. And that leads to a really interesting final question. If a two-layer PN device is a gate, what happens if you add a third layer? What kind of amazing thing could you build with a PNP or an NPN structure? Think on that for a bit, because you're on the doorstep of understanding the transistor. Thanks so much for joining me.